All right. So Shai told me that the book is now available in the bookstore. If you want to get it, you can get from, I think it's in South Campus Hall. And today we will be talking about infinite classes. So in the previous session, we proved that finite classes are agnostic, pack learnable. Previously, we had known that they are pack learnable in realizable case. Today, we are going to deal with infinite classes. So what can we say about them? Do we have an infinite class that is pack learnable? And so we need to work with simple examples. Do you have any suggestion for a very simple class that is infinite but might be easy? So I will write one. So let's consider the class of thresholds. So that's one example. So the class of thresholds is the class of all thresholds on 0, 1. And formally, that's all hypotheses in this form such that for x less than the threshold, the output is 0. For x larger than threshold, the output is 1. And R is in 0, 1. So they have one threshold. Before then, from 0 to that threshold, they output 0. They classify everything with label 0. After that, it's a 1. And it's infinite because we have infinitely many numbers, real numbers between 0 and 1. So, for example, we can draw one of them like h point half 0.5, and it will be 0 here. And 1 afterwards. So in practice, do you have any suggestion how can we learn those? Because we might somehow, we have some prior knowledge that these are the good classifiers for our problem. But they are, we have infinite number of them, so how can we deal with them? Because the bounds on finite classes doesn't work here, but still intuitively we may be able to do something. So one practical approach is to discretize. So a practical approach. And by which I mean discretizing the domain. For example, here, I can discretize the domain like that, and then I don't allow my hypothesis, the threshold to be, between those lines, but the threshold should be one of those lines. So that makes the class finite, and it could be a good approximation for the class, because for every threshold we have some hypothesis that is close to that, and it might work. So the class of thresholds with precision alpha, or with alpha number of parts, divisions, is again the same definition. But this time R is this time we just allow some discrete values for the threshold. So in practice it works. It can work, but because if you work with a computer, you cannot have continuous things usually. You need a number of bits to specify a real number. So if you store the threshold by a floating point number or something else, you may have, let's say, 20 bits to store that. So you are implicitly discrete after, and you cannot model the true thing, the exact real value. And it is similar to that idea. If we have a computer, we can say that everything is discrete, so everything is finite, and the finite bounds work. So here, I think what do you think about the size of this class? How many functions are there for a specified alpha? Yes, exactly. And we can use this bound, on the sample complexity of pack learning. But in theory, it can fail. In theory, it could not be a good approximation, by which I mean, the best hypothesis in the class of thresholds, the loss of this hypothesis could be smaller than the best one in the discretized version. Now, do you have any example that it might happen, that in such case we have one classifier in the continuous version that we cannot find a good substitute for that in our discretized version?
Well, we can have H, for instance, to be 0 on all rationals and 1 on all irrationals. And then if we discretize the rationals, which we will, because we have a fraction that alpha is rational.
Yes, could be.
So we will have, like, in our sample everything will be 0, but in reality there are many more irrationals, so the factor is pretty much 1.
That is right. So, but in order to be more accurate, we need to specify the distribution that we fail on. What kind of distribution it fails? Because sometimes you say that I have this hypothesis and I approximate it with this one, and because there is no probability mass here, they work the same on the distribution. So sometimes it's a good approximation because there is no probability between them, and they work the same on the distribution. In order to show that this happens, we need to specify a specific distribution over the. Yeah.
If all of your data is within alpha of each other, then this is possibly not a good approximation?
Yes. Yes, exactly. So within alpha, you mean within one of those discretized. Yes, 1 over alpha. Or, yes. So let's see on if the all probability mass is here, then no matter if you take this one or this one, because it's a discretized version, you need to pick this one or this one. Others are not good. And between those, we need one additional assumption. Assume that they don't have the same label. So 50% are somehow here, 50% of somehow here, and the true labeling function is this. If we take this one, we miss this 50%. If we take this one, we miss another 50%. We need to have the exact threshold to be able to do that. So just consider case that all probability mass is around Yes, that's one example. One such example that, you know, everything is between 1 over alpha and 2 over alpha, because 3 over 2 alpha and 7 over 4 alpha are both between 1 over alpha and 2 over alpha, so they are between one discretized cell, but they have different labels. We cannot say all of them are from the same class. Are you comfortable with this notation of distributions and probability masses? Because I think it is used in the book, which shows that if we have a distribution, what is the probability mass over this set? Probability distribution, I mean, that's sum of this probabilities over the members of that set. Okay. Yes?
So it shows the probability distribution over just interval?
Domain is still 0, 1, but we put all the distribution over just 2 points, 2 special points. My example is different with this because this one is a uniform here. I put everything on just 2 points, all of the distribution.
My question is that that notation means the interval between 0 and 3 over 12.
Oh, no. This is a pair, and I used it for labeled. So this distribution is D is over x times 0, 1. I will use dx for over just the domain. So this is another notation that we will use. This one is distributions marginalized over the label. The other one is the sampled distribution.
So this means, or the distribution label that you've chosen here means that there's a 50% chance that it's going to be at 0 and a 50% chance that it's going to be at 1. As in there are 2 points, there's 50% chance they will.
Yes, so 50% of the time we have the point here, 50% of the time here. And when it is here, it's all the time 0. The label is 0. And when it is here, it's all the time 1.
Right, okay.
Yes, okay. So in theory, it can badly fail. How can we still can we show that this class is pack learnable? This discretization did not work well in theory. If you carefully look at it, this one failed when we had a huge probability mass beside the decision boundary. And this could be a clue So let me draw another graph. Let this one be the true. Assume that this one is the true hypothesis, I mean true function, labeling function. We have such thing because we assume that it's the realizable case. There should be one with error 0. And we see some instances, labeled instances like these. What does ERM do here? What hypothesis it will choose? You mean average is here, like between those? Yep. Yes, it could select that, but ERM will select one that is that the error on the sample is 0. So it can basically select any function here that the threshold is between the first circle and the last point with label 0. Any of them will satisfy the ERM. But because we want to prove that ERM will work and it will be hard to work with all of those cases, we assume that our ERM selects the last point here. So this is the point. So that's ERM. So let me go here. Let our algorithm be an ERM that resolves ties in favor of the smaller thresholds. Still an ERM. And now we want to see when it fails. Intuitively, if the probability mass here is large, then the output of ERM will not be accurate, because ERM will be right here. It's the realizable case. We know that they are all 0, and at some point we will go to 1. The only place that we are not sure about is between those two lines. So here we will be also correct. In this particular example here, we will be also correct because, we did the right thing, but for the points here, we will be wrong. That's because of the certain way of resolving ties we selected. But intuitively, the problem lies here. And the amount of error is the percentage of points that are here with respect to the whole distribution. So the probability mass that is here is the amount of error. And if it is really large, we have a large probability distribution put it here, then with high probability, at least one of the examples in the sample will be in that part because it has a very large chance of being selected. That's why we can prove that the error is small with high probability. But I think we need one definition here. Let's see. Yeah, so I defined that notation for distribution over the domain, not the domain cross label. So I will use it here. So let Q epsilon be the smallest number in 0 and R such that the probability of x's in here let's work with this definition. The smallest number in 0 and R such that the probability mass from R to that point will be smaller than epsilon. So if we select the farthest point, the smallest number, then this will be more than epsilon. And if we take this one, for example, with this point, this is not the smallest number. We select the smallest number such that this is small, this probability. And now the claim is that if we have a point between Q epsilon and R in our sample, then our ERM will have error less than epsilon. If the sample contains a point in this interval, then the ERM algorithm will work well. Any ideas why it is true?
I mean, by definition, right? I mean, you're picking the point which is closer to the true function than the one which is under epsilon. So that
Yes.
will also be under epsilon.
Yes, that is right. Exactly. So we defined q epsilon in a way that it will satisfy this. And if I write it, the proof is the loss is smaller than let me define one additional thing. Let T be such point in sample. So it's the point that we were talking about in the sample. It contains a point T. So for that point, it will be T and R. Because if we have a point in our sample like this one, we will be correct all down here, and we can be wrong only here. So that's the intuition there. From T to R. And because of this, we know that T is larger than Q epsilon. Because T is larger than Q epsilon by the definition. Any questions regarding this one? Now, we just need to prove that with high probability, the error is a small for just like pack learning. So we will use this one. So that's the proof of pack learnability. We want to bound the probability that we will fail by epsilon. And we can write it like this. We said that if we have a point in this interval, we cannot be wrong more than epsilon. So the probability that we are wrong will be less than, if the probability that we have some point here. I mean, if we have a point there, then we will be right. So the probability that we are wrong is less than the probability that no example is in that interval. If we have one, we are good. And this is M, which means I generate a sample of size M. Now, because these samples are IID, we can multiply the probabilities that each of them is in that interval to compute the whole probability. So that's the IID assumption. We multiply the probabilities together, so that's where the power comes from. And between the parentheses, we have the probability that we don't hit that interval. And we have shown that it's smaller than 1 minus epsilon, which is small enough. That's just some calculations. This part from 1 minus epsilon to the m is smaller than e to the minus epsilon m. I think you have seen it in the proof of packed learnability of finite classes. But this part, this step is important. It's smaller because we proved it, that with high probability we will hit that point with probability epsilon. So 1 minus epsilon is the probability that we won't hit that interval. Okay, so what can we conclude here? Any questions?
So we're assuming here that the distribution of generating our samples is just like every point has the exactly same probability of being generated, right?
Probabilities in the domain?
Probability.
Or points in the domain?
Like the distribution which generates our sample.
Yes, it's not uniform in the domain. It's not necessarily. We didn't assume that.
But I think we have to. It could be the distribution is approaching our,
Even if the whole distribution is put here beside the threshold, then because of the same reason that we have many, it's very likely that we see a sample in that part as well.
Yeah, we could have a distribution which exponentially exponentially increases when approaches are like this.
Yes, so you're saying that if this is the true labeling function and the unlabeled distribution could be like this, right? Exponentially, you mean? That's two different things that I'm drawing in the same. So this is HR, and we have another. Let me illustrate it here. I draw another. That's d of x, the distribution over domain, the marginalized distribution over domain. I think you are suggesting something that is highly picked here, right? This is hard to find. The good threshold could be hard, or you have other suggestions.
Well, if it's bounded, then surely we'll be able to, yeah. But what if,
It could sum to 1 anyway.
yeah, no, I mean the other way around.
And it could be unique, delta Dirac, I mean infinite in just 1 point. It could be.
The distribution generating the sample.
Okay.
What if it has a really large probability of generating a sample like of small points?
Small points, you mean points to the left?
Yeah.
Okay.
So like this.
Oh, like this?
Yeah, that's the distribution generating the sample. And what if it's
What about the true threshold?
so
What?
what if it approaches the true threshold R, but it never reaches it? So basically, we have 0% of generating points after R.
Oh, I see. Like this one, right? Let's see what we have here. What will be one such sample from this distribution could be these 3 points. And ERM will say, the ERM that I define will say, this is my hypothesis, my output. And it is not that different with this one because, the probability mass here is small. So the error will be small, although we selected this one.
You can do that for every epsilon.
Yes. For every epsilon, you mean? What I mean is that if this part has some small probability, then the error will be small. If it is large, then with high probability, we will hit that. We will hit important things, and other things can be ignored. It's fine. Okay, any other questions? It means that H threshold is pack learnable with sample complexity. So with sample complexity less than any suggestions based on the bound that we found on the probability of error. We need doing some calculations there. It will be we should put, a delta there and divide and multiply things together to see that M should be larger than this to work. But this shows that the best sample complexity is smaller than this. Some finite classes are pack learnable. What about the other classes? Are all classes pack learnable? If so, then it will be nice because we can run one algorithm that can learn everything if it has enough samples. Then it will, it will be very good. And although the sample complexity might be a little bit large, but that is not that bad. For this example, it was very good.
So what happens if you relax the realizability assumption? So you say like within some range, everything is 0, and then some like delta after that, everything is 1. And then within that range, you have kind of a random distribution.
Yeah, very nice. Let me write it. We will not prove here but H threshold is agnostic pack learnable. So even if we complicate this and allow non-realizable setup where you get mixed samples. I mean, in agnostic, it's not the case that you see zeros here and ones here. They're all mixed. Some zeros here, some ones here, some 0 here, some 1 here. You need to find the best threshold with mixed things. Even in that case, it's pack learnable. It can be proved. It's not that hard. Not that easy, maybe. One idea is that saying that although there are infinite number of hypotheses in the class, many of them are very similar for a fixed distribution. And then you can make infinite finite by saying that instead of how many hypotheses do I have in the class, how many epsilon far away hypotheses do I have? Then it will be finite, and you can use union bound. But this is not what we are trying to do here. So even in that case, it's pack learnable. Now, can we conclude that other hypothesis classes are also learnable? Or
No.
okay, no, yes. Why?
They're not. I mean, there are many functions and stuff doesn't happen.
And in practice, people in practice really tend to say that it is possible. They want to build machines that work for every kind of problem.
Do we have an example problem if it's not pack learnable?
Yes.
And then we can reduce other things to it?
So that's what we are looking for. Do we have some hypothesis class that is not learnable? That's a good way of thinking. thresholds are pack learnable. What about the other thing? But if it is, I mean, if we don't have that hypothesis class, then we can learn everything, and we just give a lot of examples to our machines, and they can learn everything. But there is a class that is not learnable. And what is the hardest class to learn, if you think? Fix some size for now. Assume that the size of our hypothesis class is just 10. We have just 10 hypotheses in our class. We know that it is learnable because it's finite. But what is the, you know, yes?
Can we like pick all the functions?
Yeah, that's a very good approach. Because intuitively, when you have more options in your hypothesis class, it would be harder to learn. Because you will be compared against the best one in the agnostic setup, and also in realizable it will be harder. So yes, now we want to prove that the class of all hypothesis for an infinite domain is not learnable. That's called the no free lunch theorem. And I don't know if I have time to prove it, but let me write some. Sorry. Let X be our domain of size n. So it has size n. And let this class be the class of all functions over this domain, all possible labelings. So H in all will be all H hypotheses from X to 0, 1. But this is over a finite domain. So how many functions do we have over a domain of size n?
2 to the n.
2 to the n. So So it is pack learnable because it's finite, but that's not what we wanted to prove. So NFL, no free lunch theorem, proves that the sample complexity of learning this function for a specific value of epsilon and delta, that's 1 over 8 and 1 over 7, is larger than n over 2, half of the size of the domain. What does that mean? It means that if we see just part of the domain, I mean even half of the domain, as in our sample, then we cannot do that well. Our epsilon with probability 1 over 7, we will make error of 1 over 8. So if our domain gets larger and larger, we will need still half of the domain size to make sure that this is OK. So when the size goes to infinity, that function will not be left. So there is a corollary. The sample complexity of, I will write it like this. It shows what I mean. For infinite domain sets, the sample complexity is infinite, so the class of all functions over an infinite domain is not pack learnable. The class of all labeling functions over an infinite domain is not pack learnable. I need to explicitly say that this is the sample complexity of realizable case. Usually when we don't say, I don't know, I will, sometimes it's agnostic, sometimes it's packed, sometimes it's realizable. But if we show that even for the realizable case it's infinite, then for agnostic it will be automatically infinite as well, because it's harder. We don't have that assumption. How can we prove the main thing, the main no free lunch theorem? I mean, if we have the class of all functions, one intuition. Let me give you one intuition. If you have all possible labeling functions, even when you see half of the points and know their labels, on the other half, you don't have any idea. There could be any possible labelings on the other half of the domain. And if we assume that the probability distribution is uniform over domain, then on one half you have the sample, you can be right. on the other half, you don't have sample. You cannot do better than guessing, because everything is possible. So you may fail, 50% of the time in that part of the domain. So that's 50% of the time over half of the domain. It's 1/4 of the domain. Let me write this. So assume that we have a sample of size n/2. And assume our distribution over the domain is uniform over X. Then the learner can find out about the labels of points in Sx, the points that it's given, but for the points that are not in the sample, it cannot do better than random guessing. It cannot do better than random guessing. Because every labeling is possible on that. Because every labeling is possible on them. Therefore, it fails on at least 1/2 half of the points in, so it's an expectation. So in half of the points that is as not seen, it can fail in expectation, because it cannot do better than random guessing, and because we assume that it's uniform distribution over the domain, 1/2 of the points we had seen, 1/2 we didn't, and so it will fail on 1/4 let me write it, 25% of the points. Or some expectation is here. This is not still exact. I just tried to give you one intuition why it can fail. But the proof is a little bit trickier. We don't have time today to prove it. But it is very important result in theory that in practice it's not been appreciated well. And you really, yes?
So are we assuming the labeling is completely random?
Labeling is what?
Completely random.
No. The labeling, I assume it's the realizable case. In realizable case, there exists one labeling that we have different labelings, but I have all of the possible labelings in my class. But all of them are deterministic in the sense that, you know, it's not a coin flip. With either the label is 0 or 1. It cannot be 20% 0, 80% 1. But in the proof, I was not accurate, and I need to prove it. But the thing that I was suggesting was that because all of the labelings are possible in the second half, you cannot do, if you take one side, you say that I will pick 0 for my second half, then there exists a bad one that outputs 1. And you will fail because that one is also possible. If you, for any choice of output on the second half, there exists one bad labeling that, one possible labeling that you missed it, and your error will be large because of that. And it's just intuitively saying, it's just like saying that you cannot do that better than random guess.
My question is, like, when you are labeling, let's say you are labeling coin A, are you just doing a coin flip and then label that, or does it have some pattern?
Has some pattern. It's more, if you consider the agnostic setup, let's first work with the coin flip, 50% tail, 50% head. If you learn a classifier on that. The hypothesis is the one that outputs 1 or the one that outputs 0, I mean head or tail. But it cannot predict. No matter it says head or tail, 50% of the time it's wrong, 50% right. So the error of learner will be large, but will be similar to the best possible thing in the agnostic setup. So we are okay with that because that's inevitable. That randomness, you cannot beat it because it's the part of the nature of the problem. The Bayes optimal classifier will have error, non-zero error, will have error 0.5, which means that even if we know the distribution that is generating the data, the exact distribution, the labeled distribution, even with knowing that, we cannot do better than random guessing in that case. But that is different with this one, because here we can do better if we know the distribution. Because if we know the distribution, we know that there exists one labeling that the data is following it. And the error in the realizable case, we are assuming that there exists some labeling function in the hypothesis class that with error 0. And so did I answer your question?
But if we already have half of the sample, then can we just get some idea of the distribution?
If we have a lot of samples. Yes, so if we have more than half of the domain size, number of samples, yes, we might. Otherwise, if we have a large domain and we cannot get enough samples, just half of the domain size, then we cannot have a good estimation. So our error will be larger than 1/8 with high probability. What time is it? And I hope that Shai will prove it for you in this next section. And let me tell you another thing here. We showed that larger classes are harder to learn. The class of everything is harder to learn. But it is good in some other way. If you take a larger class, then it's more likely that there exists a good hypothesis in that class that, with a small error for the distribution. So there is a trade-off between picking a larger hypothesis class in the first place or a smaller one. If you take a very large one, you cannot learn it in the sense that although there might be good things in this large class, you cannot find them. But if you pick a very small hypothesis class, you can find the best one in it, but the best one might not be good. And they are called, we have two terms for them. Trade-off between approximation error and estimation error. So approximation error is the error of the best hypothesis in our class. And estimation error is is the error that we made because the hypothesis class was large and we couldn't find the best in the class. So for no free lunch theorem shows that for large classes the estimation error is large. For small classes, this one will be large because there might not be a good hypothesis in the class. We limited ourselves too much. Any questions?
So if we have to include all the probabilistic functions, do we get a similar thing? Or like
If we have probabilistic hypothesis, I mean the output is not a labeling but a probabilistic labeling, again, no free lunch theorem holds. You cannot do better. That large class of everything is not learnable. So yes, pretty much everything is similar.
But then you can make approximation error between 0.
No, then you need to define this in an expected way because the output is not deterministic anymore. Then you need to average in different, because every time it will output another error, different errors. So you need to average and it will be similar. Thank you.